Hey everyone, welcome to Vector Physics Podcast. I'm Isha, and today we're diving into one of the most important concepts in physics, vectors. If you've ever wondered why understanding forces matters, you're in the right place.
I'm Marcus, and I have to say, vectors seemed confusing to me at first. But once I understood them, everything in physics started making more sense. So Isha, let's start with the basics. What exactly is a vector?
Great question. A vector is a quantity that has both magnitude and direction. Think of it like giving someone directions. You don't just say, go 5 kilometers. You say, go 5 kilometers north. That's a vector. In physics, forces are perfect examples of vectors.
So magnitude is like the size or strength, and direction tells us which way it's pointing.
Exactly. And here's where it gets interesting. We can represent vectors graphically using arrows. The length of the arrow shows the magnitude, and the direction the arrow points shows the direction of the force. We use a scale to make this work. For example, we might say 1 centimeter on our drawing equals 1 Newton of force.
That makes sense visually. But what about when we have multiple forces acting on an object at the same time?
Excellent point. That's where vector addition comes in. Imagine you're pushing a box, and your friend is also pushing it from a different angle. The combined effect is called the resultant force. We can find it 2 ways, graphically and mathematically.
Let's talk about the graphical method first. How does that work?
With the graphical method, we draw the first vector at its correct angle using a protractor. Then, we draw the second vector starting from the tip of the first vector, also at its correct angle. The resultant is the arrow drawn from the starting point to the end point. It's like connecting the dots.
That sounds like something we'd actually do in the lab. Speaking of which, I remember seeing a force table in our experiment. What's that used for?
Perfect. A force table is an amazing tool for testing vector concepts. It has pulleys around its edge, and we attach strings with weights to create forces at different angles. The strings pull on a ring in the center. When a system is balanced, the resultant of all forces equals 0.
So we're actually seeing vectors in action. Now you mentioned a mathematical method too. What's that?
Yes, the mathematical method uses something called the cosine law. If we have 2 forces F1 and F2 at an angle theta between them, we can calculate the resultant R using the formula R squared equals F1 squared plus F2 squared plus 2F1 and F2 cosine theta. This gives us the exact magnitude.
That's powerful. But what if we need to know the direction of the resultant?
Great follow-up. We use another part of the cosine law to find the angle. This tells us the direction of the resultant force relative to one of the original forces, so we get both magnitude and direction mathematically.
Now here's something I've been wondering about. What's force decomposition? That sounds complicated.
Actually, it's the opposite of adding vectors. Decomposition means breaking a single force into components. Imagine a force acting at an angle. We can split it into a horizontal component and a vertical component. These components are perpendicular to each other.
Why would we want to do that?
Because it makes solving problems easier. If we know a force's magnitude and angle, we can find its x component using fx equals f times cosine angle, and its y component using fy equals f times sine angle. Then we can work with each direction separately.
That's clever. So in our lab experiment, we had 3 forces at different angles. How would we handle that?
Perfect example. We'd decompose each force into x and y components. Then we'd add all the x components together and all the y components together. Finally, we combine those sums to find the total resultant force. It's systematic and accurate.
What about real-world applications? Where do we actually use this stuff outside the classroom?
Everywhere. Engineers use vectors when designing bridges. They need to know how forces from traffic and weather combine. Pilots use vectors to calculate their actual direction when wind is pushing their plane sideways. Video game designers use vectors for physics engines. Even sports involve vectors. Think about the angle a soccer player kicks the ball.
Wow, I didn't realize vectors were so important. Any tips for students learning this material?
Definitely. First, always draw diagrams. Visualizing vectors makes everything clearer. Second, be careful with angles. Measure them consistently, usually counterclockwise from the positive x-axis. Third, practice both graphical and mathematical methods. They reinforce each other. And finally, check your work by seeing if your answers make physical sense.
That's solid advice. Thanks for breaking this down, Aisha. I feel much more confident about vectors now.
You're welcome, Marcus. Remember, vectors are fundamental to physics. Once you master them, you'll understand motion, forces, and energy so much better. Keep practicing, and don't hesitate to draw those diagrams.
Thanks for listening, everyone. This has been Vector Physics Podcast. Keep exploring the forces around you.